Welcome to Presentation 14. Today's subject will be the analog to digital converter. That's the ADC. As usual, I'd like to start by showing our architecture. The analog to digital conversion function is part of our layer 2. Now the items in green are the ones that I've already presented, and the yellow is what I'm presenting today. So the agenda is going to be as follows. First, I'm going to give you a little bit of background on the ADC, followed by a register configuration. Next, we'll have develop the framework, and finally, we'll go through a sample program. So let's get going. Now the ADC converts analog signals into digital numbers. Many sensors output analog signals. The ADC converts these analog signals into digital numbers, allowing the microcontroller to analyze and use that data. Let's look at the register configurations. So we have one register to enable the ADC. Next, we have to select the prescaler before we can use the ADC. Now the ADC clock should be between 50 kilohertz and 200 kilohertz. Now our microcontroller runs at 16 megahertz, so we need to do something. Now the ADC clock is equal to the system clock divided by the prescaler. The available prescaler, meaning that we cannot use any prescaler. We have predetermined prescaler that we must use, and those are 2, 4, 8, 16, 32, 64, and 128. Now, how do we decide which one to use? So we know that the prescaler is going to be equal to system clock divided by the ADC clock. Now, if we calculate the prescaler for a 200 kilohertz clock, then the prescaler should be 320. Now, if we do the same thing for a 50 kilohertz, then the prescaler would be 80. What that means is if we want to keep the ADC clock between 200 kilohertz and 50 kilohertz, then we need to select a prescaler between 320 and 80. And the only option that meets that requirement is a prescaler of 128. It's the only one of these available that is going to be between 320 and 80. To do this, we need to put this line of code. Basically, the AD, PS2, PS1, and PS0 is set to 1 on the ADC SRA register. Next, we have a register to start the conversion. That would be putting a 1 in the ADSC bit, which belongs to the ADC SRA register. Next, we have resolution. The conversion from analog to digital can have a resolution of 10 bits, which is used if we want higher precision, and it's the default mode. But we can also set up the resolution to be an 8-bit resolution. That would be a faster conversion and simpler to handle. However, the precision is lower precision. Now we have the digital input disable register. Disabling the digital input circuitry on the analog pin saves power, reduce noise, and improve the accuracy of the ADC. What this says is when we do the analog to digital, the signal coming into the processor is going to be an analog. So therefore, we really should disable the digital part of that input. Now, we have 6 pins that we can use for analog to digital conversion, and those are called the ADC channels. So we have ADC 0. ADC 0, it's in PC0 port, pin 23. And then there is a register, which is the max. And in that register, we need to put a value which is going to allow us to use that pin for analog functions. So the max value for ADC 0 is 0. Now we also have ADC 1, in which case we would set up the max value for 1. We have ADC 2, 3, 4, and 5. So basically we have 5 possibilities that we can use for connecting the analog signals to be converted to digital. And we have the max value, which is the ones we have to set up on the register to make that happen. Next, we need to set up a reference voltage. And we have 3 choices on how to do this. First, we can use the microcontroller 5-volt power supply, or we can use an internal 1.1 volts, which has a very high precision. And finally, we can actually hook up a voltage source which is fairly accurate to the AREF pin, which is pin 21. Now the range, if we use the microcontroller external supply power, the range is going to be a voltage between 0 and 5. Next, the configuration to make that happen is going to be setting up the ref S0 to 1 and ref S1 to 0 in the AD max register. And finally, as it relates to the ABCC, no external connection to the AREF pins is needed. Now let's look at the 1.1. The range in this case is going to be between, it's going to have to be below 1.1 volts, between 0 and 1.1. The configuration is ref S0 equal to 1 and ref S1 equal to 1 in the AD max register, and also no external connection to the RF pin is needed. Now let's look at if we plug in an external source. The range, the ADC will use voltage supplied by the RF pin as its reference, cannot exceed the ABCC. So you can input any voltage, however it has to be lower than the ABCC. And I don't say 5 volts here because sometimes some of the microcontrollers are powered by 3 volts. But in our case would be 5 volts. Next, the configuration would be, we need to set the ref S0 to 0 and the ref S1 also to 0 in the AD max register. You need to turn and extend that voltage to the AREF pins right here. Now use this reference if you need a more precise 5-volt reference or a different reference voltage, maybe 4.5, a 3, or whatever you need, as long as it's less than 5 volts in our case. Okay, now let's look at the continue to looking at the register configuration, and let's look at the ADC auto trigger. Allows the ADC to start a conversion automatically when a specific event occurs. There is no need for writing extra code to start each conversion. It ensures that ADC conversion happens at precise intervals. If it ensures that the ADC conversion happens in response to specific events. So we have two choices. Either every time we want a conversion, we set the register to start a conversion, or can be automatically. If it's automatical, for example, could be free running. That means that once you set it up, it starts calculating, I should say, converting the input voltage into a digital. Or it can be triggered by external interrupt, or a timer counter match, for example, or a timer overflow. So all these triggering, we've seen them before during the timer presentation. So let's start with our next subject, which is the ADC framework. So we're going to review first the data sheet. Next, we're going to develop the framework. To develop the framework, we create our traceability tables, and then we write the code. Before we can develop our framework, we need to review the data sheet. The data sheet is where we are going to find all the information we need for programming the microcontroller. Now this document is organized by functionality. So let's go to section 28, which contains all the information associated with the analog to digital conversion. Now let's jump to the register description. By manipulating the bits in this register, we can control the behavior of the ADC. So this first register is the ADC multiplexer section register. Here we can control which is going to be our reference voltage. We can control whether the result is going to left or right adjusted. And finally, we can control which is going to be our input channel. Next, let's go to the ADC control and status register. Here we're going to be able to enable the ADC, start the conversion, auto trigger the conversion. We're going to be able to read the register to find the status of the flags. We can enable the interrupt and also set up what's going to be our prescaler. Next, we have the ADC data register low and data register high. The result is going to be stored in two registers, and it's going to be a 10-bit resolution. Next, we have the ADC, another ADC word, which is ADC low and ADC high. Now we are going to select which data, we're going to decide how to read the data depending on whether we selected the result to be stored right adjusted or left adjusted. Next, we have the ADC control and status register B. So this is where we decide what's going to be our mode for triggering the conversion. We have the different possibilities. And finally, we have the digital input disable register 0. Once we decide what's going to be our input port, then what we want to do is disable the digital function so we can reduce the power consumption. So I think with this, I've given you a general understanding of what's contained in the data sheet and where you can find the information. So let's go ahead and put together our framework. Okay, so let's continue with our framework. So as usual, what I do is I take information from the data sheet and then I write the code that goes with that data. So in this case, we have the ADC control and status register, and then in this place, based on this information, I write this code. Next, we continue with the this has the function name, which is the register, and this is the bit name associated with each bit in the register. And based on that, I write the code. And this is the code that I'm going to put together to create the framework. So the framework will be implemented as an include file, and we have here framework _ADC.h. Now, the source code is generated by extracting the content of column code. So this is what I wrote in the column code, and I copy and paste and created the framework. To prevent any naming conflict with existing development environments, the parameters names have been modified by adding an X in the front. Basically, as I always say, the environment does this for you, but I've decided to create this to give you a background of where things come from. And sometimes you may not have an environment that will do this for you. Finally, as a side effect, we have created traceability to our source code back to the data sheet. Now let's look at our sample program. So let me start with the schematic. So we have the microcontroller. We have 5 LEDs hooked up to port B0, B1, B2, B3, and B4. And then we have a potentiometer hooked up to our analog input ADC1. So the idea is that as I move this potentiometer, the analog input to the controller changes between 0 and 5 and is converted from analog to digitals. And we're going to turn an LED dependent on the voltage. So let's look at the sample program. External potentiometer will be connected to the microcontroller and provide between 1 and 5 volts. 5 LEDs will be connected to the microcontroller. The resolution from analog to digital conversion will be a 10-bit resolution. Interrupts will be implemented to trigger each time a conversion is completed. The interrupt routine will turn on or off LEDs to represent the input voltage. Each LED will represent 1 volt. So let's look at the source code. First, I'm going to give you a global view of the program. So we have here a routine to initialize the port, a routine to initialize interrupts, a routine to initialize the ADC, our main program, and then we have an interrupt service routine that gets triggered every time a conversion is completed. So let's look at the detailed code. So we're going to have 5 LEDs hooked up to the microcontroller. Therefore, what we do here is we set pin B0, pin B1, 2, 3, and pin B4 to outputs. And the LEDs will be hooked up to those ports. Next we go to the init interrupts. What we do here is we enable the interrupt that is going to be triggered every time an ADC conversion is complete. And that's what this line of code does. And next we enable the global interrupt, which is this command. Now let's go to the init ADC. With our first line of code, we're going to disable the ADC digital input buffer because we're going to use the ADC1 pin for an analog input. Therefore, a good procedure is to disable that digital input buffer. Next, our potentiometer is going to be hooked up to ADC1. So we have to set up the input channel to be ADC1, and to do that we need to set the AD max to 0001, and that's what these 4 lines of code are doing. Next, we enable the ADC. Then we need to set up what's the value of the prescaler. We know that the prescaler maximum value has to be 320 and the minimum is going to be 80. So the only value that fits those requirements is the 128. So we set up the prescaler to be 128, and that's what this line is doing. Next, we set the ADLAR to 0, which means that the result is going to be right adjusted. Next, we set up the ADC voltage reference to be the microcontroller input voltage, and that's done with these 2 lines. And finally, we start the conversion, or we set up the command to start the conversion. Now let's look at the main program. The main program, what it does is initialize the ports, initialize the ADC, initialize the interrupt, and then it goes to infinite loop. Now every time there is a conversion, I should say every time a conversion is completed, the interrupt service routine will be triggered. Now let's look at what this routine is doing. So the first thing it does, it reads the conversion result low from the ADCL. Next, it reads the conversion result high from the ADCH. And then it puts those 2 numbers, converts it into the conversion result by placing the conversion result low on the first 8 bits, and then takes the conversion result high and shifted 8 spaces. Now, next step, we're going to calculate the value of the voltage, which is going to be the conversion result times 5 divided by 1023. The result from here, from this calculation, can be 1 volt, 2, 3, 4, 5, or the default is 0. Now the first step we do in each of our case is we set up all the lights to 0. We turn them off, and then we turn on the one that should be turned on according to the voltage. And finally, we start the conversion again. Because every time there is a conversion, we need to restart it again. So for 1 volt, we turn on 1 light. For 2 volts, 2 lights. For 3 volts. For 4 volts, we turn 4 lights. And for 5 volts, we turn 5, I should really say, LEDs. And every time, after turning on every LED, we command the ADC to start conversion again. And then the final is the default, which sets all the LEDs to 0. Now, I think with this, I've given you a good idea how this works. So we had the potentiometer changes the voltage. Every time the voltage is changed, there is an ADC conversion. And once that conversion is complete, it triggers the conversion complete interrupt, and we end up in this interrupt service routine. And then we have a case which, according to what the input voltage, will turn 1, 2, 3, 4 or 5 LEDs. So with this, I think you have a good idea how the analog to digital conversion works. So we got to the end of today's presentations. Today I gave you some background on the ADC. We developed, or I should say, I gave you some information on how to set up the ADC register. We developed the framework, and finally I went through a sample program. I hope you've enjoyed this presentation, and thank you very much.